In this section, we'll be focusing on reactions in solutions, and we're going to start with looking at mostly water in this instance. We can also have solutions in as gas form, but we're going to focus most of the things that are done typically are going to be done in water, and this is one of the most important common compounds and dissolves a lot of different substances. That's why we're going to focus on these processes of dilution and solutions in typically using water solutions. First, we need to define some terms, and we need to look at the difference between a solvent versus a solute. So a solvent can be anything that your solute is going to be diluted into. So typically in this instance that we're talking about water, it's going to be water. You can have organic solvents. You can have things like different types of ethanol, for example, can be a solvent where things would dissolve in ethanol. So if we take ethanol or alcohol and you put a vanilla bean in there, right? Your vanilla compounds will dissolve into your ethanol. So the solvent would actually be ethanol in that instance, and your solute would be that vanillin. That's the chemical compound that is coming out of vanilla beans. So your solute is the thing that's dissolving in the thing that has the most volume is typically your solvent, and the smaller amounts are going to be your solute. So in order for things to interact and react, there has to be a physical contact between two elements. And when you solvate a compound in a solution, that makes it more freely available, right? Obviously, if it's a powder sitting on the ground somewhere, it's not going to necessarily react with another powder sitting further away. So once water comes in, and those can mix together freely, and there's a better chance for chemical reaction. So there's different types of solutions. We're going to talk about homogeneous mixtures where there's components are completely mixed in and you couldn't tell individual components, versus heterogeneous mixtures where there are kind of chunks or there are separate components that you can kind of visualize and identify. We're just thinking about a cup of coffee that has milk and sugar in it. What's the solute? What is the solvent? And I want you to just think about this, and we'll look at the options here. So pause here, just make sure you're on the same page as me, and then we'll go on to the next slide. So of course, coffee, we put water in the coffee that is going to dissolve the components from the coffee bean. So there are different things in coffee, some of the flavors, but caffeine's certainly in there unless you have decaf. Sugar, you have the milk and the proteins that are in the milk and maybe fats. So that's all going to be dissolved in our coffee. And interestingly, one of the ways that we can actually get out caffeine, there are multiple different ways. There are chemical extractions or there are heating mechanisms, but you're actually dissolving the caffeine out of your coffee beans, and then you're kind of leaving some of the flavors behind, but you're just decaffeinating it. So that's an interesting process that you might want to look more into, but it's also using these same ideas. In this chapter, we're also going to start talking about concentrations in certain volumes. So if these things are dissolved in liquid, right, you can see that we have the solute here and the solvent. The solute is in a very dilute concentration in the left vial here, or the left beaker, and in the right beaker, it's a lot more concentrated. So we're going to talk about that, and it's kind of a similar idea. It's not the same, but it's a similar idea to density. If we're just looking at the density of the solute in the left beaker versus the right beaker, the density of the solute is more dense in the left than the right. Obviously, the overall density is not going to change that much because we have, if we also have to consider the density of the solvent as well. But it's when we're looking at these in the future, it's kind of similar, a similar idea. Examples of dilute solutions might be eye drops or saline solution. That would be like the left beaker, and pickle brine would be a lot more concentrated. If you had, depending on how you like your coffee, right, you might have no sugar in there, or you might have a lot of sugar in your coffee. So we start with unsaturated solutions and we can eventually get to a saturated solution. And the saturated solution is essentially the point at which we have so much solute that we don't then have enough, that we've maximized the capacity for the solvent to encompass it and keep it in solution. So if we get over that, so let's say we add a bunch of salt in here and then we mix it up and then we keep adding salt, at some point you're just going to get a pile of salt on the bottom of this beaker because the water molecules are not going to be able to solvate or encompass and surround your salt. When we look at different types of compounds and their solubility, their different salts, for example, are going to be soluble at different amounts. And typically to look at solubility, we'll look at the grams of the solute that make a saturated solution in 100 grams of solvent. And these are going to be temperature dependent. The reasoning for that is when you put a salt in solution, it's dissolved, and when it's warmer, the water is going to be able to move faster. It has more kinetic energy. It's going to move around and have more of an ability to interact with the solute. And then you can have more of that in solution, and the solvent can cover more of that space. Here are some examples of different solubilities for sodium chloride. 35.7 at 0, but you can get a couple more grams in there at 100 degrees Celsius, around boiling. Sodium hydroxide, the solubility is even better, 42 grams at 0 degrees Celsius and 347 grams at 100 degrees. So increasing the temperature for sodium hydroxide is very beneficial for its solubility. When we look at calcium carbonate, is very low solubility at about room temperature. So different salts will have different solubilities. They'll interact in different ways, and that is going to be represented here by that solubility factor. You could, of course, do supersaturated solutions if you've ever tried to make rock candy, where you heat up your water, you add sugar into that water, and it's super saturated. So at boiling point of water, you can get a lot more sugar in there, and then you let it slowly cool down with a stick or a string in it, and then that sugar will start to crystallize on that string, and then you'll be able to get something like this where you can make that rock candy from a super saturated solution. As it starts to cool off, it will precipitate out. So that's this idea of a precipitate. And again, it's a product. So if you have two liquids and you mix them together and they interact, those salts in the two different solutions interact, they'll form a product that has low solubility. So it's not something that was insoluble already in your liquid. It's something that formed out of the liquid after a chemical reaction. And we'll look at a few examples of precipitation reactions. And here's one looking at lead nitrate. And this is AQ, means that it's in the aqueous form, so it's in solution. You can see that lead nitrate in this beaker here is soluble. It's just a clear liquid. And 2 units of potassium iodide, also aqueous, which means it's in solution. And that reacts to form lead iodide, which is a solid, which then you can see as these are poured together, you can see this turns into a yellow liquid, and that lead iodide is the solid compound, and then 2 units of potassium nitrate, which is in the aqueous form. So this is just a kind of still floating around in solution. So this is the final, this is the ionic formula. So you have the lead nitrate, these groups break apart into their separate ions, and then you have the potassium iodide. These are going to break apart into those ions, and then there's a rearrangement. It's also called a metathesis reaction, where we swap partners. So the lead, the positively charged lead, goes to the negatively charged iodide. Positively charged potassium goes with the nitrate, and we're left with this solid lead iodide. Okay, so we're going to look at another example here. We have this chemical reaction, silver nitrate, ammonium carbonate, react to form ammonium nitrate and silver carbonate. Which is the precipitate in the following reaction? So answer this and post your answer on Blackboard. So this is an example of a compounds in water. We talked about that rock candy with sugar. So this is just a cartoon image of sugar. This is the actual molecular makeup of sugar. Here you can see that some of the sugar is dissolving in water, and if it's dissolved, it's completely surrounded by water. And if you have a chunk of sugar on the bottom of your glass, it's not going to be yet dissolved. And this in order for it to be dissolved, you have to have those particles completely surrounded by your solvent. When we look at salt dissociation, this is an example, kind of another cartoon of the sodium chloride. And again, you can see that the sodium here is in the blue, that's the positive ion, and the chloride ion is the negatively charged ion, and it's completely surrounded. So this would be a situation where you'd have a chunk of sodium chloride salt on the bottom, and then you'd have a few pieces that were ionized. So this is kind of the chemical reaction that would show you that happening of these falling apart into the aqueous solution. I should make a note on polyatomic ions. Those remain intact. So they're one group. Like this is sodium chloride. This is just two atoms that are falling apart into ions. But if we have something like potassium iodate, the potassium falls off, but the iodate is the polyatomic, so multi-atom ion. So this is a unit that has an overall negative charge, and this is just an atom that has a positive charge. So these polyatomics, we had covered these a few chapters previous, but there are groups of these that will commonly kind of fall apart as units. So what is the difference between ions and molecular compounds dissolving? Well, there's actually an important difference, and we can look at that difference through looking at running electrical currents through the solution. If they have these full positive or negative charges, or if they're just soluble for other purposes, if they, for example, have intermolecular forces that allow them to be soluble into the water. So an electrolyte is something that falls apart into a full ion, and it allows electrons to kind of flow through that solution. So you can see copper sulfate is that blue solution. The copper sulfate is turning this water blue, and when we run an electric current through there and attach that to a light bulb, we can actually get current flow through those electrodes. If we put sugar in there, sugar doesn't create ions in water, so we get no light, even though we still have that electric current running through that sample. Electrolytes are solutions that yield electrically conducing ions, and strong electrolytes will dissolve 100% in water, and they'll be really great at conducting that electricity. So if we're going to look at a lot of times you're not supposed to be swimming in water in a lightning storm, for example. Water that is out in a lake will have a lot of these dissolved salts in the water, typically, unless it's pure deionized water, which we don't have anywhere probably in Wisconsin that you'd be swimming in. It's going to conduct electricity pretty well. Pure water doesn't conduct electricity very well. It has to have these kind of ions in it in order to do that. I have a little cartoon here that kind of shows you what's actually happening. We have enough copper in solution, and this is able to move around freely. These copper +2 compounds, these atoms, have spaces in their electron orbitals. And electrons from one of these electrodes to the other can kind of jump over through these positively charged spaces, and they can flow through that solution from the left to the right, for example. You can kind of see that happening in this process here. All right, what do you think here? Would electricity flow better through a dilute solution or through a concentrated solution? And why do you think that would be? Post your answer in our Blackboard space. So just to distinguish between a strong electrolyte, a weak electrolyte, and a non-electrolyte, this is an example of sugar that we looked at before. And you'll notice these molecules hold their electrons close to each other. They're sharing them between these different atoms, and they don't fall off. There are no charges that are on here. There are differences in electronegativity between, for example, the carbons and the oxygens here. So we'll have partial positive charge, partial negative charges. We have flowing of electrons from the carbon to oxygen, and then also from the from the hydrogen to the oxygen. So we do have these partial charges that help to make this soluble, but there's no full charges. There are not electron orbitals available for electrons to flow through here. So we can't put an electrical current. It's not, there's no extra space. There's just a little bit of movement within the molecules, but there's no full-on orbital that's available to flow through this solution. Okay, I want you to think about how many ions form in the dissociation of this compound. And just as a kind of hint, this phosphate group is a polyatomic. So post your answers in the Blackboard space, and then I'll move on to the next kind of steps here. One more I'd like you to look at, aluminum sulfate. These are going to break down. And if you remember, I'll just solve this one for you and go back to the other one if you're not sure. Remember those subscripts? They are going to, we use those and crisscross them in order to identify the charge. The first unit is always going to have a positive charge. We give, if you're going to give someone feedback, constructive feedback, the positive news always comes first. That's kind of how I like to look at it. So you give them a positive news and then the negative news. So aluminum is going to have a positive charge, and that charge is going to be 3, a +3. And then we have a sulfate that's going to be SO4. It's going to be negatively charged. It's going to have a -2. So these subscripts are how many of these are in solution, right? So we have 2 of these aluminum ions, and then we have 3 of these SO4 units. And so 3 of these. And you'll notice, oops, sorry about that, I have the wrong charge here. And we have the overall charge. We have a 2, 4, we have the, 2, 4, and 6. So we have a -6 charge. And then we have a 3 plus a 3, so that's a +6. So you notice that these charges cancel out. So that is the reason that we have those subscripts there, is to make sure that that unit of our compound, our ionic unit, is going to be an equally neutral charged unit. And so this crisscross rule helps us to figure out what those charges are going to be so that those charged states can cancel out. Strong versus weak electrolytes can tell us something about that state of the compound that we're dissolving in our water. Hydrochloric acid is going to be a really strong electrolyte, which means that it falls apart very readily in solution. When we look at something like this acetic acid, or we're talking about the ammonia here, these are weak electrolytes, and it tells us that they like to stay more as molecules, but sometimes one of these, for example, these hydrogens on here, it acts more like an acid, and it's going to donate to water that proton. So we have a little bit of that happening. And then if we look at ammonia, that's even a weaker electrolyte. So even less time, you can see that is happening even less often with the ammonia in forming NH4 ions. So this can tell us something about the state of the compounds and how well they ionize in water. One of the big differences between some of these things that we are going to think about as strong electrolytes or weak electrolytes, non-electrolytes, are if they consist of metals like sodium, aluminum, calcium, and then groups of polyatomics and nonmetals. So these are groups of nonmetals here that are going to make up that second group. This is a polyatomic. Here is actually a metal and a nonmetal. But if we have metals and nonmetals grouped together, that's going to tell us that they're probably going to be stronger electrolytes, and they're going to form ions in solution. So when we break these apart, we can use that same idea of looking at these polyatomics, and we can do the crisscross rule that's an inferred one. So we can see that we'd have 3 sodium ions, and they're going to have a single positive charge. And we have 1 potassium ion that has a -3 charge. And remember that has to balance. So we have a neutral compound here. We have 3 +1 charges and 1 -3 charge that gives us that neutral charge state. If we look at aluminum sulfate, we do the same crisscross idea here. We'll have an aluminum that will have 2 of these. That's that subscript says that we have 2 of them. The charge is a +3, and then we have 3 sulfate groups with a -2 charge. So 3 times 2 is going to give us a -6. 2 times plus 3 is a positive 6, so those cancel out. So I'd like you to do the next two, calcium chloride and the calcium permanganate, and write those reactions down for the number of elements, like we did 2 and 3, and then the charge for each of those as well. Post that in our Blackboard space. I just want to give you a quick overview of some of the ways that chemists write down equations. One is we can write these in as molecular equations. So there are no charges, everything's just put together in terms of those units that will fall apart potentially into ions. And here's an example of lead nitrate, potassium iodide, potassium iodide, lead iodide, and potassium nitrate. And these are all put together, and they're good for planning experiments and making predictions for what is going to happen. You can see that these react to form a solid lead iodide and then an aqueous potassium nitrate. You can also write this out in the ionic equation. We're going to break those all apart like we were practicing doing. And you can see that those lead nitrate and potassium iodide, I broke those apart into their ionic form. So these are all aqueous. And so the only thing you have to make sure you're doing is if it's an AQ behind the molecular equation, for example here, then you can break those apart here, here, and here. But the lead iodide, we cannot break apart because it's saying that's a solid. So you'll notice in the ionic equation that we kept that one together. The net ionic equation is kind of the third thing that you can do. And essentially what we're doing is we are taking that and we're going to look at things on both sides of the equation that really don't do anything. They're just kind of there. So the potassium isn't really doing anything. The nitrate is on both sides. It's not doing anything, right? There are two of them. So we're canceling out the same number of ions on both sides. And then what we're left with is the lead ion and the iodide ion and the solid. So that's where we get these different terms. And then this is the net ionic equation. So it's a simplified equation. These things that we canceled out are called spectator ion. And they're just kind of there. They could be really anything. We could have any negatively charged thing theoretically. We could have a chloride on the ion there. We could have some other ions that are involved. They're not really doing too much in this reaction as long as they don't interact and form a precipitate. So those are just kind of there, but they're not involved in the chemical reaction. And just remember, when we're working with chemical equations, we have to have a material balance. So if we have a number of atoms, if we have a number of chlorine atoms or potassium atoms, they have to be the same number on the left and the right hand side of that arrow. Because if we had different amounts, that would mean that we somehow lost or gained matter. We lost or gained mass, and that can't happen. The electrical balance also has to be preserved. So if we have something on the left, and it doesn't matter if the overall charge is different. So this example here, we have a -6 and a +2, so the overall would be a -4. And on the right side, we have a +4 and a -8, so it's a -4. And that's okay. It doesn't have to be 0. But you can't have, for example, a -2 does not equal a -3. That doesn't work. And really what charges are telling us is the number of electrons that are involved. And if you gain or lose electrons, you're really gaining or losing matter. And we can't do that. In chemistry, that's not something that happens. That's not something we predict would happen. So you can't add or remove electrons from a chemical equation. That doesn't work. It has to remain balanced. Just to practice this, I would like you to look at these 5 different equations. I want you to tell me which one of these 5 is not electrically balanced and post that in our Blackboard space. And that's where I'll stop for this section, and we'll continue on with solutions with another video.